Hi everyone, welcome back. Today we're going to start our new unit on bonding. And the first thing that I want to talk with you guys about in our new unit is ions. Ions are really important because they combine into a lot of different reactions and become parts of many different things that we see and use every day. So let's get started in our notes about ions today. So ions, okay, really important. Simply though, known as an atom that has a charge. And what we already know about charge, since we've already talked a little bit about ions in a previous unit, is there's a different number of protons and electrons. Okay, so they can be positive or they can be negatively charged. So two different possibilities for our ions. And we're going to take a look at both of these types of ions. So that atom has either gained or lost electrons. Okay, so if it has lost electrons, it's going to be a positively charged ion. If it's gained electrons, which we know are negatively charged, it's going to become a negatively charged ion. So why should we study ions? Okay, the charge of an atom determines what other elements and in what combination that atom can combine with to form new compounds. Okay, as I mentioned, a lot of ions we see and use every day. Salts are a really big one, a really common one that we see and use all the time. Ions are in our body and things like that. So a lot of exposure we have to ions daily. So two types of ions, as I mentioned, positively charged and negatively charged. First one I want to look at is a positively charged ion. So a positively charged ion lost electrons, and if it loses those electrons, it loses those negatively charged particles. Okay, the overall charge of that atom is now going to be positive. This is known as a cation. Okay, a cation, positively charged, and these are typically metals. Okay, metals have more electrons in their outer shell, which we'll get a little bit more into that as we go here. But metals become cations. If an ion or an atom gains electrons, okay, if it gains electrons, it's going to then be negatively charged. We call this an anion, okay, negatively charged, and these are characteristic of nonmetals. Okay, a good way to remember an anion is it's a negative ion, okay, a negative ion. So one of the things that we want to look at to determine if an atom is going to become negatively charged or become positively charged is we want to look at the valence electrons. You may have heard this term before and you may not be clear on what a valence electron is, but we're going to try to go through it here a little bit today. But a valence electron are electrons that occupy the highest energy level. And if you remember in our last unit, we were talking about quantum theory and energy levels of electrons and things like that. Well, that's going to come into play here as we're looking at our valence electrons. Okay, those valence electrons are found in the s and p orbitals. If you remember, as we were writing out our electron configuration and orbital notation, okay, the highest energy levels, right, were always ended up being in the s and p orbitals. Okay, I don't know if you picked that up as we were going through that stuff, but they're always in the s and p orbitals. Those DNF orbitals end up being 1 or 2, respectively, energy levels lower than where those s and p orbitals are for each row on the periodic table. So those valence electrons then determine how an element bonds with other elements. Okay, so for example, carbon, okay, we know it's 1s2, 2s2, 2p2. So we can take a look at this electron configuration and determine how many valence electrons there are. The highest energy level is 2, okay, and that is found again in the s and p orbitals. And we see that there are 4 valence electrons in carbon, okay, 4 valence electrons. Another example, bromine, okay, bromine is one of those non-metals. So we can already know just from that whether we can assume this will be an anion or a cation. So bromine, okay, is going to be an anion. If we write out the shorthand version of the electron configuration, we see that the highest energy level is the fourth energy level. And in those s and p orbitals, okay, we're not counting the d orbital because that's in the third energy level, right? Just the highest energy level. So 4s2 and 4p5. Add those up, we get a total number of valence electrons for bromine of 7 valence electrons. Okay, and we're going to look at how this comes into play here. So because the number of valence electrons in an element is the same as the group number for that element. Okay, so just for the representative elements, so 1A through 8A, right? We're talking about the elements that fall into the S and P sublevel blocks on the periodic table. For example, okay, group 1A, if we look at the periodic table, all of those alkali metals all have 1 valence electron. Group 2A, the alkaline earth metals, all have 2 valence electrons, and so on. So group 4A all has 4 valence electrons, and we can keep going on that way for all of those groups on the periodic table. So we want to take a look at, we have a way that we can actually draw out those valence electrons to help us determine how that ion or atom will bond with other atoms. So this is known as electron dot notation, also called Lewis dot diagrams. So let's take a look at how we do this. So this is used to represent those valence electrons in that atom. So what we do is first we write the element symbol. Then we draw dots around that symbol. The number of dots should equal the number of valence electrons for that atom. Okay, for example, helium. Okay, we know helium has 2 valence electrons. So I could write the element symbol and then draw 2 dots for the 2 valence electrons for helium. Okay, nitrogen. We know nitrogen has 5 valence electrons, and chlorine, okay, chlorine, one of the halogens in the 7A group, has 7 valence electrons. So I would then draw those 7 electrons, okay, and I pair those up on each of the 4 sides on there. Okay, this will help us when we look at bonding in our next couple of videos and how that works. So we want a stable electron configuration. And what I mean by a stable electron configuration is that atoms react by changing the number of electrons that they have. They want to have a stable electron configuration, which we know the noble gases, okay, the noble gases are not very reactive because they have a full set of valence electrons. That outermost highest energy level shell is full, okay, so it doesn't readily gain or lose electrons. Well, other elements want to be like the noble gases, so they react in a way that allows them to behave as though they have a full valence electron shell. This is called the octet rule. So the octet rule says that atoms tend to gain, lose, or share electrons in order to acquire a full set of valence electrons. We'll get into some other types of bonding after we talk about ions where they share those electrons, but for now, we're going to look at how they gain and lose those electrons to fit into the octet rule. Okay, they want to look like that nearest noble gas. So first thing that we need to do is we need to form an ion. So if an atom has 3 or less valence electrons, they will tend to lose those electrons and become positively charged. Okay, these are those positively charged cations, those metals that we talked about. Okay, if an atom has 5 to 7 valence electrons, they will tend to gain electrons in order to fill their valence shell. Okay, gaining all those electrons, gaining negatively charged particles, it will become an anion, a negatively charged ion. And a good way to remember this, if you want to think about it, we know that a valence shell has 8 electrons in it. If I see that an element or an atom has 3 valence electrons, in order to have a full valence shell, is it going to take more energy to lose 3 electrons or to gain 5 electrons? Right? It's going to take less energy to lose those 3 electrons than it is to gain those 5 electrons. So if you're not sure and you can't remember which one, how that atom is going to behave, think about the amount of energy that it takes to gain and lose those electrons. So once it gains or loses those electrons, that atom becomes an ion. It has a charge, and the charge is determined by the number of protons compared to the number of electrons in that ion. So if the protons are greater in number than the electrons, you have a positive ion, okay, or a cation, right? More protons, more positively charged particles than negatively charged particles, right? 1 to 1, they cancel out. But when there is more positively charged, you'll get a positive ion. If you have more negatively charged particles or electrons, okay, then you do protons, it will become a negative ion or an anion. Okay, and the actual charge, we can assign a specific charge to these ions depending on how great that difference is between protons and electrons. So the difference between the protons and electrons is also the charge on that ion. Okay, so let's take a look at a couple examples here. So nitrogen, we know, has 7 protons. Okay, it also has 7 electrons. So in its standard state here, there is no net charge. Okay, it is not an ion. But we can draw this. Okay, we know if we write out the electron configuration, we know it has 5 valence electrons. We can also look at the periodic table and see that nitrogen is in the 5A group on the periodic table, which also tells us that there's 5 valence electrons. So we'll write nitrogen and draw the 5 valence electrons in our Lewis dot structure. Okay, for the nitrogen ion, we want to have a full valence shell. So with 7 electrons, it gains 3 to become like the nearest noble gas, which in this case is neon. Okay, so it has to gain 3 electrons. So on the periodic table, if we look at that, neon is 3 spaces to the right of nitrogen. So it needs to gain 3 electrons to be like neon. Okay, so 7 protons. Now we have 10 electrons after that nitrogen atom gained 3 electrons. But now we have a difference. Okay, there's a difference of 3 electrons. So if there's 3 additional negatively charged particles, our net charge on this ion is -3. Okay, and we write this as N3 minus. So we use the symbol for the atom, and then we put 3 minus. Now, not -3, it's 3 minus charge. Okay, when we draw this as our Lewis dot structure, okay, we add those 3 electrons, we put it in brackets, and then we put the charge outside the brackets. Okay, we'll have a worksheet that we'll do where you'll be writing these Lewis dot structures of the ions. So make sure to take good notes on this, okay, because we will be doing this. All right, on the periodic table, I also recommend getting a periodic table, shading in the different groups, and writing the charges on these. These are the ones that you will need to know. So, +1 charge for the alkali metals, +2 charge or 2+ charge for the alkaline earth metals. Okay, boron and aluminum have a +3 charge. Okay, and then we work back the other way. -3 charge for group 5A. Group 6A has a -2 charge, and the halogens then have a -1 charge. So if you take a look here, there's actually a pattern. Why don't I have carbon and silicon and that group labeled? Well, those have 4 valence electrons, and since they're right in the middle, right, we were talking about the amount of energy it takes to gain and lose electrons. Since they're right in the middle, they can go either way. So we're not going to worry about those as far as ions are concerned right now. We'll look at carbon and silicon and how those behave at a later time. A couple other things that you need to know. Okay, silver and gold, those are metals, so those are also going to be cations. Those have a +1 charge. And zinc, another cation, another metal, has a +2 charge. So I recommend you make sure you get these down in your notes because these are the ones that you're going to need to remember. The specific groups, those should be fairly easy to remember. Zinc, silver, and gold, those ones you might need to write down and kind of memorize those because we'll be looking at those a lot. So our electron dot notation for ions, okay, is just a pictorial representation of ions as we just looked at with nitrogen. So Lewis dot diagram for ions shows the added or removed electrons. We're going to do an example here of an anion and a cation. Okay, it also shows the charge of the ion. So we'll bring back nitrogen. We have our 5 valence electrons for nitrogen. We add 1, 2, 3 electrons, put it in the brackets, and put our charge outside the brackets. Let's take a look at a cation here, sodium. Okay, sodium has how many valence electrons? That's right, 1 valence electron. Okay, but that valence electron goes away. So we no longer write that valence electron, right? It loses an electron. We then put the brackets out and a +1 charge on the outside of the brackets. Okay, this nitrogen anion, okay, all anions will look like this. All anions that we write will have 8 valence electrons shown in the Lewis dot structure. Same thing with all cations, except that they will have no electrons shown in their Lewis dot structure of cations. Okay, so all of these will look like this inside the brackets, depending on what element we're looking at there with the charge outside. So one last thing that I want to look at for ions today is how do we name ions? Okay, it's actually fairly simple, right? There's just 1 or 2 little things that we change when we're naming ions. So for cations, okay, these are those positively charged ions again, okay, those lost electrons. The name is the same as the element, except we add ion. That's all we have to do is just add ion to the name of the element. Okay, for example, okay, hydrogen, if I have a positively charged hydrogen ion, we simply name it hydrogen ion. Okay, sodium is known as sodium ion. Magnesium, magnesium ion. Thing I want to note here is it doesn't matter what the charge is. You notice hydrogen and sodium both have a +1 charge, and you may have noticed that there isn't in fact a 1 there. If the charge is 1, whether positive or negative, okay, you don't have to write the 1 there. Magnesium, 2+ charge, doesn't affect the name compared to sodium and hydrogen ions. Okay, just want to make that distinction there. So let's take a look at our last thing, anions. How do we name an anion? It's a little bit different. Okay, so an anion, again, gain those electrons. It's negatively charged. We change the suffix of the element to "ide." Okay, this may seem familiar to you when we look at some of these. Okay, for example, a fluorine that has gained electrons is known as fluoride. Okay, chlorine is chloride. Okay, oxygen is oxide. Again, it does not matter what the charge is and how great the negative charge is there. We see fluoride and chloride, those 2 halogens have a 1- charge, and oxide has a 2- charge. Does not affect the name. Just knowing that it's an anion, we simply change the suffix to "ide." So that is all that I have for you guys today on ions. I hope this has been helpful to you guys, and I look forward to discussing this more with you moving forward and talking about how these ions actually bond in our next topic. So until then, have a great one. Thanks.